And the actual method of what I'm going to show you is not tough. Okay? The level of what we're going to go to as we move through this is going to get tough, okay? Because remember, we have to be able to integrate anything, right? Do we have the ability right now to integrate anything? Well, some of you guys have suggested backwards power rules or backwards product rules and backwards quotient rules and thought about it like that, right? And that's usually what I would expect people to think. But what I'm actually going to do is show you a way to sort of take all of that into account, okay? Because if you looked at something like this, and I said, okay, well, I want to take the derivative of this, right? Well, if I want to take the derivative of this, what immediately comes to mind? What rule? Chain rule, yeah, because there's an interior here, right? In fact, it looks like it's multiple chain rules, right? So if you remember, when we use the chain rule, we always start with the innermost, and we work our way out, right? So the innermost thing would be this, correct? And is it differentiable? So we would differentiate it, and we would get 8x Let me change the battery. Maybe that's the problem.
Here's
Austin. For what?
graduation stuff.
Oh, is
Yeah.
it? All right. Oh, well, that wasn't helpful, like at all. There we go. All right, so we go the innermost, 8x. All right, then we go to the e. Well, how do we differentiate something e to the x? It's e to the x. All right, and what is the derivative of tangent? Secant squared. So then it's secant squared of the interior. Everybody cool, right? So we took a derivative, awesome. And we remember how to do that, beautiful, right? Because that's about as difficult as a derivative as we really ever had to take, right? Something using a chain rule like that, right? Multiple chain rule, pretty intense. Well, how does it work backwards? How do we go from this back to here? Oh, I'm sorry, from this back to here, right? How do we take an antiderivative of this? And this is the technique I'm going to be showing you guys today. Well, with one like this, it's really intimidating, isn't it? Right? I mean, there's like a lot going on. So what I want you to do is I want you to think about this problem sort of like, is there an interior, is there an inside of this function? Well, there's a secant squared, that's inside, and there's an 8x, that's not really inside, that's on the outside. Is there something that's the most interior? The e to the 4x squared. Yeah, well, there's and I would even say, well, maybe the 4x squared, okay? But for sake of discussion, let's just say it's e to the 4x squared, okay? What I'm going to do is I'm going to call that u. Now, by me calling that u, I can do what? I can do a little replacement and substitution, right? So if I was to substitute, oh, by the way, one other thing. Actually, I'm not going to do that yet. Okay, so when I substitute, I have 8x times u times secant squared of u dx. All right. What's concerning about what I just wrote down? There should be something that you're concerned about. Two variables. And the problem is that I'm supposed to be what? Taking an integral with respect to x. So how am I going to do that when there's things with u's in it? Agreed? All right. Well, is this something that I can take a derivative of? A derivative. Can I take a derivative? Sure. D over dx equals, well, what's the derivative of e to the 4x squared? Well, the derivative of 4x squared is 8x. And the derivative of e to the x is e to the x. How are we doing? Agreed that I can actually multiply both sides of this by dx. So if I did that, how would it read now? It would read du equals 8x e to the 4x squared dx. Still okay? All right. I want to go back up to here for a minute. What if I didn't make this a u? What if I left it the way it was? Then it would have said this. Correct? Now check this out. 8 x e to the 4x squared. E to the 4x squared. Dx. So what can I do? Well, can I take this and this and this and substitute in a du? Seem reasonable? Okay, Brandon, this yellow term, and this yellow term equals this, right? Well, can I replace these three things with a du? Okay, so I'm going to do that. Everybody see what I did? Okay, now hang on a minute. What's inside the parentheses here? Another thing with a what in it though? An x, right? Well, check it out. Isn't this the same as this? So what can I do? Can I put a u in for this term? And why is that great news? Because now what's in this integral? Only u's. What's the integral of secant squared? Come on, Brandon, you know it. You just gave me the other one. Tangent, right? So this is going to be tangent of u plus c. What was u again? E to the 4x squared, right? So now what am I going to do? Plug it back in. Yeah, plug it back in. And where did that bring me, guys? Well, it brought me back to what? What we started with, right? Now, what's the only issue? It's going to be some multiple of that, right? Because of the c, right? I'm never going to be able to go right back to this because we always have the possibility of there being some constant, right? See the issue? Yeah. So we can get really, really close to being the same, but we never know that we're actually the same. All right, so we're going to do a lot of work with this. okay? This concept of U-substitution, okay? We're going to start with some things that are really, really simple and get to some things that are really, really complex, okay? Don't worry about what this is saying here. We're going to talk about unpacking. I'm going to use some of this terminology as we start looking at some of these problems. All right, guys, if I look at this problem and I said, guys, I want to take an integral of this. Well, what's something that you think your original equation had in it? Just give me thoughts. I'm taking an integral of this. So what do you think this antiderivative had in it? Great, that's what I was looking for. Something to the 13th power, right? Okay. Well, what was probably raised to the 13th power? X squared plus 1, right? Now, Brandon, the problem with this being a 13 is when I take the derivative of the outside using a chain rule, I'd wind up with a 13 in front, right? So I got to correct that. 1/13, right? 1/13. And then if I think about taking the derivative of this, right, you recognize this is a chain rule problem, right? So I would say, okay, take the 13, bring this in front. I'd write this again, drop it by 1, and then I'd take the derivative of the inside. And what's the derivative of the inside? 2x. So that's actually exactly what we were looking for, isn't it? Plus c. Guys, that's just called pattern recognition, right? You know what these look like when you do an antiderivative, but we got to get kind of lucky too, right? You know what I mean by we got to get kind of lucky, Austin? Like, what are the chances that this is going to work out perfectly the way this did, right? So we got to get kind of lucky. So pattern recognition is a way to go about doing it, but we can also do this using a method of U-substitution. And the U-substitution method is kind of nice also. So U equals, what would you probably make your U in this problem if you had to guess is the most interior piece? X squared plus 1. Now, Gardner said 2x, or she was going to say 2x. But if you think about the method of U-substitution, I know that I'm going to wind up taking a derivative of this. And what is the derivative of this going to give me? 2x. Something. Now, it's really, really nice that it's 2x, right? But I definitely know it's something to the x, to the first power, right? So I'm really feeling good about making this my U. Everybody kind of comfortable why? Okay. So the derivative of U, oops, with respect to x is equal to 2x. And I'm going to leave it like that for a minute. We'll talk about y later on. And I'm going to rewrite my original problem, right? So what is my original problem going to look like now? Well, it's an integral of go ahead, tell me what you think. U to the 12th, good. All right, so I got a U to the 12th. Now, I got this, right? I got to get this. Is there any way I can get this to look like this? Multiply both sides by dx, right? And why is that great news? Because this matches this, which means I can substitute in a du. Well, this is super easy to take an integral of, right? What's the integral of this? Well, raise it, correct it, add my constant. And what did we say U was? Don't even ask the question yet, okay? Don't even ask the question yet. Does the general concept make sense, right? The general concept, kind of cool, right? We've only gotten 2 examples in, so if it's not something you're totally comfortable with, that's certainly what I would expect. All right, so here's an example. Let's take a look at it. All right. Guys, there are going to be a ton of little tricks that we're going to talk about as we do these. Okay. There are going to be a ton of little tricks. Now, part of this, guys, is thinking ahead. Okay. What would you recognize as probably the interior? 2x to the 4th plus 1. Now, I know I'm going to need to take a derivative of this, right? And by taking the derivative of this, what will I wind up getting? 8x cubed, right? Now, kind of good and kind of bad. Kind of good because I got the x cubed. Kind of bad because I got an 8 and a 3. Those don't match, do they? Okay. So we run into our first sort of roadblock, right? Okay. But for now, what do you guys know I can do with this 3? It's a constant multiplier, right? It's a constant multiplier. So let's put that in front. Let's at least do that much. All right, and you guys suggested that we want to use 2x to the 4th plus 1 is our u. Well, the derivative of that is 8x to the 3rd. Austin, can you close that door for me? Thanks, man. All right, ready? This is where it's going to get kind of cool. Do you guys agree that right now I could rewrite this as that? Fair to say? Okay. Now you guys know that if I'm using U-substitution, I only want what to be here? U's. So what do I got to get rid of? I gotta get those 2 things out of there, right? Well, is there any way I can get this to look like this? I want it to say x cubed dx. So tell me what to do. Sure you can. Give me something. Give me one thing that's going to make it look more like that. Move the what? Move dx over. There you go. Divide by 8. Now it matches, doesn't it? So what can I do? I can substitute x cubed dx with du divided by 8. And hey guys, what do you think I'm going to do with the divided by 8? Move it to the outside. So now it's 3/8 integral sine u du. Can you believe that we took this, right? And we turned it into a problem where we only have to integrate sine of u. Pretty cool, right? What derivative gives me sine? Negative cosine. Very good. All right. So now I just substitute back in. So I have -3/8 cosine of 2x to the 4th plus 1 plus c. What do you guys think so far? Kind of neat, right? Kind of a cool way of doing it. So Brandon's question is relevant. Can I do this for everything? Well, you can do it for a lot of them. And when I look at problems, guys, like this is where our algebra skills really start to fly. Again, I want you to think about how crazy we're already doing something with an integral in it. If I asked you guys to integrate this yesterday, you would have looked at me like I had 16 heads, right? And you would have said this better be a calculator problem, okay? But again, let's see if we can do it. If you had to guess as to what you believe you're going to make your U value, what is it going to be? Okay, so I hear a radical, the cubed root. So you think you want to take this whole thing. All right. Let me ask you this. Is there anything I can do right now to make this a simpler problem? 1/pi, right? So let's at least think along those lines. Oh, by the way, what might be a reasonable thing to do right now also? Rewrite that as a what? As a fractional exponent, right? Yeah, let's rewrite it as a fractional exponent. What's the exponent? 1/3. Good job. All right. What could I do here? Well, anybody want to reevaluate what you think your U value is going to be right now? X squared plus 2x. And why would you use x squared plus 2x? Because the derivative of that is 2x plus 2, and at least I have the right degree of the x value, right? That's kind of what I'm looking for, right? I want to make sure I have the one that's going to give me the correct degree, okay? So yeah, let's go with U being x squared plus 2x. All right, derivative of that is 2x plus 2. All right, you guys want to at least make a substitution here to get going, and then we'll see what we gotta adjust. All right, so my question is, what stuff do I want to remove from my integral so I can take my integral? The x plus 1 and the dx, right? I don't want those to be there. So how do I get this to say that? Okay, so Brandon wants to move dx over. Brandon wants to divide by 2. Okay. When I divide by 2, what do I get? Equals x plus 1 dx. Beautiful. All right. Awesome. So what's going to happen? I'm going to rewrite this as 1/pi. integral of u to the 1/3 du over 2. Now what? Yeah, move the 2 to the outside. So now it's going to be 1 over 2 pi integral of u to the 1/3 du. Now what? Integral. Yeah, now it's I haven't taken the integral yet. Yeah. What's the integral of u to the 1/3? Add 1, right? So I'm going to add 3/3. So the power is 4/3. Now I got to correct it. So what do I put in front of that? 3/4. But what was already in front of everything? 1 over 2 pi. What do I got to remember not to forget? Plus the c, right? And now I can substitute the u back in, right? So this is 3 over 8 pi. What is this going to be here? This is going to be the cubed root of u to the 4th power. Plus c. Do you have any idea how awesome you guys are if you can integrate this by hand? I mean, that's this process right here. Who agrees this process is freaking dope, man? I mean, look at this. Look at what we just integrated. That's crazy. Makes me feel good about myself, Raymond, that I can do that problem. It really does. Okay, now in each of these problems, guys, I'm going to have the exact same value of u. Okay? Anybody want to venture a guess as to what that value of u is going to be? Take a minute, look through them, see if you can figure out what the value of u is going to be for each of these. All going to be the same. Close. Cosine of 2x, yeah. Yeah, the u value for all of these is going to be cosine of 2x. What about the e? E to this. Well, oh, we'll get to that. It's an identity. Yeah, it's an identity. What's the derivative of this? Careful, it's a chain rule. 2. Not 2, but negative 2, right? Because derivative of cosine is negative sine, right? So negative 2 sine of 2x. That cool? Are we good with that? All right, so what are we going to do, guys? Well, we're going to take our function and we're going to at least do our substitution and figure out what we got to do, right? Give me the first thing we're going to do here in this example. Move the 5, agreed. So we'll move the 5. All right, so now I have sine of 2x. Is that a substitution or am I going to leave it for now? I'm going to leave it. And then I have e to the u dx. So what am I looking to do? I'm looking to find the substitution for this with this, right? This is close. What's the only issue that I got? The negative 2, right? So what am I going to do? I'm going to move the dx over, and then I'm going to divide by negative 2, right? So do you guys agree? In this problem, du divided by negative 2 is equal to sine of 2x dx. So that's our substitution, right? So 5 integral of e to the u times du divided by -2. What am I going to do next? What am I going to do next? Move the -2 over, right? Yeah, so this is the same as 5 over -2 integrals of e to the u du. What's the integral of e to the u? E to the u. Plus c, right? And all I got to do now is plug the u back in. This was like, guys, believe it or not, when I do homeworks, calc homeworks and notes and things like that, I go through the same perils as you, right? I hit the same roadblocks. I know when the assignments are difficult, okay? What's really great about this entire lesson, which is going to take us a few days, is that we do so much review of derivatives and integral and integration techniques. We see a ton of stuff. We're going to look back at the antiderivatives for the trig functions and for the inverse trig functions. So we're going to see that again. So it's a good like review lesson, really. All right. So again, we know that we're using this, right, to do our problem. Okay. So let's just write this. All right, going to rewrite my integral. Give me something I can rewrite. Bring the 7. Sine of 2x. Can't do anything with that yet. And what do I have here? I have cosine of 2x to the 2/3 power. Does that sound okay? So isn't that really just this? Everybody see it? All right. And don't forget the what? Don't forget the dx, right? All right, what am I trying to do, guys? I'm trying to get this. Same exact scenario as last problem, right? All right. Oops. All right, what we're going to do to our power. I can integrate it now, right? I'm going to add 1 to it. What's the power going to be? 5/3. What's my correction going to be? 3/5. But don't forget what was already there. That, right? So what do I got here? I got 21 over -10. And then I have the cubed root of cosine to the 5th of 2x plus c. Impressive work, isn't it, Brandon? All right. I was kind of silent right there. How does that catch your fancy? Everything there seem okay? Right? Just kind of set things up like we did in the last couple of problems. And what do I need to do? Well, again, I need this, which is the same issues we had on the last couple of problems, right? So that's going to be the same as that, which is the same as that. Integral? One-third u cubed. So what do I have here? I have negative a third cosine cubed of 2x plus c. A lot of things got to go right for this to work, right? Are we recognizing that? Like these are usually set up for us to work kind of nicely. Yeah, so we'll have some strategies. Yeah, we'll have some strategies for that. Why don't you guys take a few minutes? I want you to try E. I want you to try. Where'd it go? Why is it gone? Oh, there it is. I want you to try D and F, and this right here, guys, cosine squared of x minus sine squared of x. Okay. Well, okay, so I know, Brandon, right? But this is like one of those sheets that I told you, you really want to know. All right, I'll give you guys like 5 minutes to try those 5 problems or 3 problems.
Wow, your class is so small.
Shh, don't say that. Nobody notices.
taking out in front.
Mm-hmm.
I thought so, but then it didn't work, so I just did it.
What's that? It's just cosine 2x.
Isn't sine of 2x and cos of 2x?
Yeah, but why would you need to just keep using the same method? Same method. Don't change your method. All right, let's see how we did. So, let's go through it. I'll let you guys correct first if you made any mistakes. Thoughts? How did we do on that one? If we made mistakes, where were they? Okay. You just didn't think to do any derivative. Okay. Fair enough. Make sense though?
I just didn't finish it.
Okay. All right, so what did I do in the first step? I replaced this with this, right? So that was the identity. So that's where this came from. And then I took the 2/3 because that's a fraction. They can come out in front, right? Those are constant multipliers. Get them out of there. So I have 2/3 of sine of 2x over radical fifth root of cosine of 2x. So what I did is I just brought that up top. Let's make it look nice. So there's my u. There's my sine 2x of dx. So there's my substitution for that. Brought the -1/2 in front, which is where the -1/3 came from. And then took my integral of u to the -1/5. All right, here's the last one. Last one was actually kind of easy.
Wait, can you make it so we can see both E and
Yeah.